Close your eyes for a moment. Imagine you are sitting in a quiet room. Outside your window, the air is still. The sky is clear, not a cloud in sight. No signs of a storm, no warnings, no hints of what is coming. And yet, in 2 days, someone will know exactly what the weather will be. They will know it will rain. They will know it will be windy. They will know it will be cold. How? They did not look at the sky. They did not check the clouds. They did not consult ancient wisdom. Instead, they did something far stranger. They took a piece of paper and a pencil and started counting, adding, subtracting, multiplying, rows upon rows of numbers. They tried to compute the weather, the way one might compute the trajectory of a cannonball or the orbit of a planet. And they failed, spectacularly, catastrophically. But from that spectacular failure, the greatest story you have never heard began to unfold. The story of how human beings learned to see the invisible, to predict the unpredictable, and to turn chaos into mathematics. The story of the physics of weather. Have you ever wondered why the weather forecast is always a probability? Why, with billions of dollars and decades of technology, meteorologists still say 60% chance of rain? Why can we send humans to the moon but cannot say with certainty whether it will rain 3 days from now? What if this is not a failure of technology? What if it is a fundamental property of the universe itself? What if the weather is structured in a way that makes it impossible to predict with perfect accuracy? Or is it possible? This script is not about how weather works. It is about how we came to understand how it works. And what that understanding tells us about ourselves, about mathematics, and about the very nature of reality. We will travel from law to laws, from guesses to calculations, from old sayings to equations, and we will discover that our struggle to understand the weather is really a struggle to understand the very fabric of existence. You know what tomorrow will bring. You can feel it in your bones. Or maybe you simply noticed that the sky this evening is particularly red. Red sky at night, sailor's delight, the old sea captains used to say. Red sky in morning, sailors take warning. You may never have been a sailor, but you have heard this phrase. And there is truth in it. It works. Sometimes. Before meteorology became a science, before people invented words like cyclone and anticyclone, before anyone knew how to measure air pressure or humidity, there was law, an oral tradition passed down through generations, a set of signs and rules that helped people survive. And it was not just superstition. It was the first primitive, utterly vital attempt to understand the weather. Think of a farmer from 3,000 years ago. He could not check a forecast on his phone. His crops, his very life, depended on whether he could guess when the rains would come. So he watched. And he remembered. If ants build their mounds high, it means a harsh winter is coming. If swallows fly low, rain is on the way. If dandelions close their petals, it will rain soon. These observations were his only weapons against uncertainty. And there was wisdom in them. Swallows fly low because the insects they eat drop closer to the ground before rain, when the air grows heavy and damp. Dandelions close their petals to protect their pollen from moisture. Every folk saying is not magic. It is careful observation of the delicate connection between the physics of the atmosphere and the behavior of living things. But law has a fatal flaw. It tells you what will happen. It never tells you why. Why does a red sky predict good weather? Because that is what grandfather said. And grandfather was right. Most of the time. But sometimes he was wrong. And when he was wrong, it was a disaster. This is where our journey begins. From these ancient signs to modern supercomputers, from belief to knowledge, from law to laws, but between them lay a vast gulf. To cross it, human beings had to invent something entirely new, a way to measure the invisible, a way to record what cannot be touched. And that invention happened in Italy in the 17th century, and it began with a glass tube and a pool of mercury. The year is 1643. Evangelista Torricelli sits in his workshop, staring at an upside-down glass tube partly filled with mercury. He is a student of Galileo, and he is obsessed with one idea, the idea of emptiness. In ancient times, philosophers believed that nature abhors a vacuum, that the universe cannot tolerate the absence of matter. If you create a void, they said, nature will fill it with anything, rather than leave it empty. Torricelli doubted this. He took a glass tube, sealed at one end, filled it with mercury, closed the open end with his finger, turned it upside down, and lowered it into a bowl of mercury. When he removed his finger, the mercury in the tube did not drain completely. It dropped to a certain level and stopped. Above it, there was empty space. He had created a vacuum. Nature did not fill it. The emptiness remained. But then what was holding the mercury up? Torricelli's answer was simple and brilliant. The mercury was not being pulled up by the vacuum above. It was being pushed up by the air below. The atmosphere, which no one had ever seen or felt, has weight. It presses down on the mercury in the bowl, and that pressure forces the mercury back up into the tube. A column of mercury about 30 inches high is the weight of the entire atmosphere pressing on every square inch of the surface below. This was the moment when weather became measurable. Torricelli had invented the barometer, the first instrument that could see the invisible. And soon, scientists noticed something strange. The column of mercury was not always the same height. In clear weather, it rose. Before a storm, it fell. Atmospheric pressure changed, and these changes preceded changes in the weather. For the first time, a person had a tool that could predict the weather not by folklore, but by precise measurement. In 1662, before anyone could explain why, Robert Boyle recorded, "I have noticed that when the mercury in the barometer falls, a storm almost always follows. Not the other way around. The storm does not cause the fall. The fall precedes the storm." This was the first observation of a cause and effect relationship between pressure and weather. But this observation explained nothing. Why does pressure fall? What makes it change? The barometer showed what was happening. It did not show why. Answering that question would take centuries. The barometer was the first step. It showed that the atmosphere is not an abstract concept. It is a physical system with measurable properties. But it remained a system that no one understood. It was like a giant clockwork mechanism where we could see only one hand. All we knew was that air has weight, and that its weight changes. But how does it change? Why does it change? And can it be predicted? The answer to these questions did not come from meteorologists. It came from physicists studying the behavior of gases. It came from laboratories where people tried to understand how steam engines work, how heat turns into motion. This answer lay at the very foundation of physics, in the field called thermodynamics. Thermodynamics is the study of heat, work, and energy. And its laws apply to everything, including the air around you. By the mid-19th century, physicists knew enough to start putting the puzzle together. Air is a gas, and gases obey certain laws. The most famous is Boyle's law. If you compress a gas, its pressure increases, and if you heat a gas, it expands. All of this was known, but how did it connect to the weather? The answer came from a French engineer named Sadi Carnot. He studied steam engines and asked a simple question. What is the maximum amount of work you can get from heat? His answer changed everything. Carnot showed that work happens only when heat flows from a hot place to a cold place. Temperature moves from high to low. And in that movement lies energy. Now picture the atmosphere. The Earth is heated by the sun, but it is not heated evenly. The equator receives more heat than the poles. Warm air at the equator expands, becomes less dense, and rises. Cold air at the poles contracts, becomes denser, and sinks. Movement follows. Air flows from where there is more of it to where there is less. This is wind. Carnot showed that the atmosphere is a giant heat engine. The sun heats some parts of the Earth more than others. A temperature difference appears. That difference creates a pressure difference. That pressure difference creates movement of air. This movement, which we call wind, tries to even out the temperature, moving heat from the equator toward the poles. But there is a complication. If the Earth did not rotate, wind would simply blow from the poles to the equator in a straight line. But the Earth does rotate, and this rotation creates a force that causes moving air to curve. In 1835, a French engineer named Gaspard Gustave de Coriolis described this force mathematically. Every moving object on a rotating planet is deflected from a straight path. In the northern hemisphere, it curves to the right. In the southern hemisphere, it curves to the left. This is the Coriolis effect. It affects not only ocean currents and cannonballs, it affects air. And it turns simple wind into cyclones and anticyclones, spinning great spirals across the planet. Now the puzzle began to fit together. The atmosphere is a heat engine running on temperature differences. Wind is the movement of air from high pressure to low pressure. The Earth's rotation twists this flow into spirals. All of this can be described by physical laws. But there is one problem. These laws are differential equations. They describe how pressure, temperature, density, and wind speed change at every point in space and time. To predict the weather, you would need to solve these equations for the entire atmosphere simultaneously. And that is impossible, at least by hand. The person who first understood this, and the first who tried to do it, was a Norwegian physicist whose name is almost forgotten today. But without him, there would be no weather forecast, no alert before a storm, no planning your week around the rain. He was a man with a vision, so bold, so ambitious, that it would take nearly a century and the invention of the digital computer to realize it. His name was Vilhelm Bjerknes, and his story begins in Oslo in the year 1904. Vilhelm Bjerknes stood before a hushed auditorium and declared that weather could be predicted mathematically. It sounded like madness. Weather was chaos, whimsy, unpredictability. How could it be written as equations? But Bjerknes insisted. He was a physicist, trained in electromagnetism and fluid dynamics. He knew that the behavior of liquids and gases can be described with precision. The atmosphere is simply a gas. It must obey these laws. And if it obeys laws, it can be predicted. But there was one catch. To predict the weather for a single day, you would need millions of calculations. By hand, it would take years. Bjerknes knew this. He was not proposing to start immediately. He was proposing a concept, an idea of what could be done someday. But someone read his work and took it literally. He said, "I will do it. I will calculate the weather by hand, with a pencil and paper." His name was Lewis Fry Richardson, and his story is one of the great tragedies, the great obsessions, and perhaps the greatest failure in the history of science. Richardson was a Quaker, a pacifist, and a mathematical genius. He worked at the British Meteorological Office and was consumed by Bjerknes's vision. In 1916, as the First World War raged, Richardson was drafted. But he was a pacifist and refused to carry a weapon. Instead, he was sent to France as an ambulance driver. And there, in his spare time, between ferrying the wounded from the battlefield, he began his calculations. He sat in his cab, sometimes under shellfire, and he computed, adding, subtracting, multiplying. Step by step, he tried to calculate the weather over Germany. He created a grid, a vast lattice covering Europe. In each cell, he recorded pressure, temperature, humidity. Then, using the equations of physics, he calculated how the state of the atmosphere would change after a certain interval of time. It was a Herculean effort. In 1922, Richardson published his book, Weather Prediction by Numerical Process. It laid out his entire method, and it included one example. He had calculated how the weather over Central Europe would change over 6 hours. The result was disastrous. His forecast predicted a pressure change of 145 millibars, a colossal, unimaginable shift. In reality, the pressure changed by less than 1 millibar. He was off by more than a factor of 100. Richardson's work was met with scorn. He was called a madman. His method was ridiculed. His book was ignored. Richardson was crushed. He left meteorology and never returned. But he was right. His calculations were correct. He had simply used the wrong starting conditions. There were tiny errors in his measurements, fractions of a degree, fractions of a millibar. These tiny errors grew during the calculations into catastrophic differences. Richardson did not know that he had stumbled upon something far more fundamental than inaccurate data. He had run headlong into the very structure of the universe, into something that, 40 years later, would be called the butterfly effect. The idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. And that is where our story goes next. To a computer lab in Massachusetts, to a man named Edward Lorenz, and to the discovery that chaos is not the absence of order, but a different kind of order altogether. Let us pause for a moment and think about what it means to predict the future. Every day you make predictions. You predict that the sun will rise tomorrow. You predict that the coffee you just poured will be hot. You predict that the chair you are about to sit in will hold your weight. These are predictions based on experience, on patterns you have seen 1,000 times before. They feel like certainties, not guesses. But weather prediction is different. It is not about patterns you have seen before. It is about equations, about physics, about understanding the invisible forces that shape the world around you. And the person who first understood this, who first dared to imagine that weather could be reduced to numbers and computed like the orbit of a planet, was a quiet Norwegian physicist named Vilhelm Bjerknes. Bjerknes was born in 1862 in Christiania, which is now Oslo, Norway. His father was a physicist, and young Wilhelm grew up surrounded by scientific talk. He studied in Paris and in Bonn, and he became one of the leading physicists of his generation. But he was not interested in the usual topics of the day. He was not interested in electricity or magnetism or the structure of atoms. He was interested in something far more elusive. He was interested in the movement of fluids. Fluid dynamics is the study of how liquids and gases flow. It is the physics of rivers and oceans, of smoke rising from a candle, of blood pumping through veins. And it is the physics of the atmosphere. In the late 1800s, physicists had already developed elegant equations that described fluid motion. The Navier-Stokes equations, named after the French engineer Claude Louis Navier and the British mathematician George Gabriel Stokes, were a masterpiece of mathematics. They described exactly how a fluid moves under the influence of pressure, gravity, and friction. Bjerknes looked at these equations and had a vision. The atmosphere, he realized, is a fluid. It obeys the Navier-Stokes equations. If you know the state of the atmosphere at one moment, you can calculate its state at the next moment, and the next, and the next. Step by step, you can calculate the future. This was a radical idea. In 1904, Bjerknes presented it to the world. He stood before a meeting of scientists in Rome and declared that weather could be predicted mathematically. He called it numerical weather prediction. The reaction was not what he had hoped. People were skeptical. Weather was too chaotic, too complex, too influenced by forces we could not measure. How could you possibly calculate something so vast and so changeable? The equations might be perfect in theory, but in practice, they were useless. Bjerknes knew this. He knew that the calculations would be enormous. To predict the weather for a single day, you would need to know the temperature, pressure, humidity, and wind speed at thousands of points across the globe. And then you would need to solve the equations for each point, for each moment in time. It would require millions of calculations. By hand, it would take years. But Bjerknes did not care about the practical difficulties. He was a visionary. He believed that someday, somehow, humans would build machines capable of doing these calculations. He believed that the future belonged to computation. He planted the seed, and someone picked it up. His name was Lewis Fry Richardson, and he was not a visionary, he was an obsess. Richardson was born in 1881 in Newcastle upon Tyne, England. He was a Quaker, a pacifist, and a genius. He studied mathematics at Cambridge and then joined the British Meteorological Office. He was fascinated by weather. He had read Bjerknes's work and was captivated by it. But Richardson did not just admire Bjerknes's vision, he decided to make it real. In 1916, the First World War was raging across Europe. Richardson, as a pacifist, refused to fight. Instead, he was sent to France as a driver for the Friends ambulance unit. He spent his days driving wounded soldiers from the front lines to field hospitals. He spent his nights doing something far stranger. He spent his nights calculating the weather. He would sit in his ambulance, sometimes under enemy fire, and he would compute. He had a notebook filled with numbers. He had a grid of points across Europe. At each point, he wrote down the temperature, the pressure, the humidity, the wind speed. Then, using the equations of fluid dynamics, he calculated how these values would change after a small interval of time. Then he did it again, and again. He called this process computing. But remember, this was long before digital computers existed. There were no machines. There was only Richardson, a pencil, and a stack of paper. He was the computer. For 2 years, Richardson worked on his calculations. He refined his methods. He developed techniques to make the computations faster and more accurate. He dreamed of building a room full of people, all doing calculations in parallel, like a giant mechanical brain. He called it a forecast factory. It was a beautiful, mad vision. In 1922, Richardson published his work in a book called Weather Prediction by Numerical Process. It was a masterpiece of ambition. It laid out every step of his method. It described how to set up the grid, how to apply the equations, how to handle the boundaries between land and sea. It was the blueprint for all future weather modeling. And then Richardson did something extraordinary. He included an example. He showed how his method could predict the weather over Central Europe for 6 hours. He started with the conditions at 7 in the morning and calculated what they would be at 1 in the afternoon. The result was a catastrophe. Richardson's calculation predicted that the atmospheric pressure over Germany would drop by 145 millibars. In reality, the pressure barely changed at all. He had overestimated the change by more than 100 times. The error was so massive, so absurd, that it seemed to prove the opposite of what Richardson intended. It seemed to prove that numerical weather prediction was impossible, that Bjerknes had been wrong, that the atmosphere was beyond the reach of mathematics. Richardson was devastated. His book was met with silence. A few scientists read it and dismissed it as the work of a madman. Richardson himself left the meteorological office and never worked on weather prediction again. He moved on to other things. He studied the causes of war, the psychology of conflict, the mathematics of arms races. He became a respected scholar in his own right. But he never returned to the weather. And yet, Richardson had not made a mistake. His calculations were correct. The equations he used were the right equations. The method he developed was the right method. The problem was not his math. The problem was his data. To do his calculation, Richardson had used the best data available in 1922. But that data was not perfect. There were small errors in the measurements. A fraction of a degree here, a fraction of a millibar there. These tiny errors were barely noticeable. But when Richardson applied his equations, the errors grew. They multiplied, they amplified. By the end of the calculation, a tiny error had become a massive disaster. Richardson had stumbled upon something profound, something that no one in his time fully understood. He had encountered a fundamental property of the atmosphere. It is what mathematicians call a chaotic system. A system so sensitive to initial conditions that even a microscopic error can produce a catastrophic difference. This property is now known as the butterfly effect. It was discovered by another scientist, Edward Lorenz, 40 years later. But Richardson had felt its sting first. He had failed not because he was wrong, but because he was too early. His calculations were correct for a perfect world, but the world he lived in was not perfect. His measurements were imperfect. His data was incomplete. And the atmosphere took advantage of every tiny flaw. The tragedy of Richardson is that he was right. He was so far ahead of his time that he could not see the finish line. The tools he needed did not exist. The computers, the satellites, the global observation networks, none of them were there. He was trying to build a cathedral with a child's toy hammer. But Richardson's vision did not die. It waited. It slept. And when the technology finally caught up, his ideas were resurrected. Today, every weather forecast you see is based on Richardson's method. The grid is finer. The data is better. The computers are unimaginably faster. But the principle is exactly the same. You start with the state of the atmosphere. You apply the equations of physics. You calculate the future, step by step, moment by moment. In a sense, every time you check the weather on your phone, you are looking at the ghost of Lewis Fry Richardson, the man who failed so spectacularly that he became a cautionary tale, the man who was right all along. But Richardson's story is also a warning. It shows that prediction is not just about having the right equations. It is about having the right data. And it is about understanding the limits of what data can tell you. Because even with perfect data, even with perfect computers, the atmosphere remains chaotic. The butterfly effect means that there will always be a limit to how far ahead we can see. We cannot predict the weather forever. We cannot know with certainty what will happen in a month, a year, a decade. The future is not written, it cannot be, but we can predict probabilities. We can say, there is a 60% chance of rain tomorrow. We can say, there is a high probability of a storm in 3 days. And that is enough. That is more than enough. That is the difference between chaos and disaster. Richardson did not know this. He thought he could eliminate all error. He thought he could achieve perfect prediction. He was wrong. But his wrongness taught us something important. It taught us that the limits of prediction are not failures. They are features. They are built into the fabric of the universe. And that is where our story goes next. To the discovery of chaos, to a man named Edward Lorenz, to the realization that the universe is not a clockwork mechanism, but something far stranger, far more beautiful, and far more unpredictable. The butterfly had not yet flapped its wings, but it was about to. In the early 1960s, a meteorologist named Edward Lorenz was running simple computer models in his office at the Massachusetts Institute of Technology. He was not trying to predict the weather. He was trying to understand how the weather worked. And one day, he made a small mistake. He typed in a number that was rounded off to 3 decimal places instead of 6. The difference was tiny, less than 1/1000th of a unit. But when he compared his new results to the old ones, they were completely different. The tiny error had grown into a massive divergence. Lorenz spent weeks trying to understand what had happened. And what he discovered would change not just meteorology, but our entire understanding of the universe. He discovered that the atmosphere is a chaotic system, that small causes can have large effects, that the future cannot be predicted with certainty because the present cannot be known with infinite precision. He called this the butterfly effect, and it became one of the most famous ideas in modern science. The year is 1961. The place is the Massachusetts Institute of Technology, the sprawling campus along the Charles River in Cambridge, just outside Boston. In a small office, cluttered with papers and printouts, a man sits staring at a computer printout. His name is Edward Lorenz. He is a meteorologist, but he does not study the weather outside his window. He studies it inside his computer. Lorenz has built a simple mathematical model of the atmosphere. It is not a realistic model. It does not include oceans or mountains or the full complexity of the real world. It is a toy model, a set of 12 equations that capture the essential physics of how air moves. But it is enough. It is enough to show something remarkable. One day, Lorenz decides to run a simulation again. He has been running the same simulation for weeks, watching how his model atmosphere evolves over time. But this time, he wants to save time. Instead of starting from the beginning, he takes the printout of a previous run, finds the numbers from midway through, and types them into the computer as new starting conditions. He expects the new run to match the old one exactly. After all, it is the same model, the same equations, the same numbers. Mathematics is deterministic. Identical inputs produce identical outputs. That is one of the most fundamental principles of science. But something strange happens. The new run starts out close to the old one. For a few minutes, the numbers match, but then, slowly at first, they begin to drift apart. The divergence grows. Within a few simulated days, the 2 runs are completely different. They look like 2 entirely different weather systems. Lorenz is baffled. He checks his data, he checks his calculations. Everything seems correct. And then he notices something tiny. The numbers he typed in were not exactly the same as the original numbers. On the printout, they were rounded to 3 decimal places. In the computer's memory, they were stored with 6 decimal places. The difference was minuscule, less than 1/1000th of a percent. But that minuscule difference had led to a massive divergence. Lorenz had discovered something profound. The atmosphere is what mathematicians call a non-linear system. In a linear system, small causes produce small effects. You can predict the outcome with confidence. But in a non-linear system, small causes can produce huge effects. Tiny errors grow over time, eventually overwhelming the system. Lorenz spent years thinking about this discovery. He gave lectures about it, he published papers, and then, in 1972, he gave a talk with a title that would become legendary. He called it, "Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" The phrase caught the public imagination. It became known as the butterfly effect. It was a poetic way of saying that the weather is so sensitive to initial conditions that even the tiniest disturbance can eventually produce dramatic changes. The butterfly does not actually cause the tornado, of course. But the metaphor is powerful. It captures the essential idea that the future is not fixed, that small events matter, that the world is more interconnected and more fragile than we ever imagined. Lorenz's discovery had profound implications for meteorology. It meant that perfect weather prediction was impossible. Not because our models are bad, not because our computers are slow, but because the atmosphere itself is chaotic. Even if you knew the exact temperature, pressure, and wind speed at every point on Earth at this instant, you could not predict the weather with certainty a month from now. The errors in your measurements, no matter how small, would grow until they overwhelmed the forecast. This was a hard truth for meteorologists to accept. For centuries, people had dreamed of perfect prediction. The ancient Greeks had tried to read the future in the flight of birds. Medieval farmers had watched the signs of the seasons. Victorian scientists had built elaborate instruments to measure every aspect of the atmosphere. And now, in the 20th century, with computers and satellites and global observation networks, we seemed closer than ever to achieving the dream. But Lorenz showed that the dream was impossible. The future is not written. It cannot be known with certainty. Not because we are not clever enough, but because the universe does not work that way. This did not mean that weather prediction was useless. On the contrary, it meant that we had to change the way we thought about prediction. Instead of trying to forecast a single definitive outcome, we had to forecast probabilities. Instead of saying, "It will rain at 3 o'clock," we had to say, "There is a 60% chance of rain." This was not a retreat, it was a refinement. It was a recognition of the true nature of the atmosphere. It was also the birth of ensemble forecasting. Ensemble forecasting is a clever idea. Instead of running a single model once, you run it many times with slightly different starting conditions. You introduce tiny variations into the data. You change the temperature by a fraction of a degree. You adjust the pressure by a tiny amount. You run the model 100 times, each time with slightly different initial values. Then you look at the results. If most of the runs predict rain, you can say with confidence that rain is likely. If the runs are split, you know that the forecast is uncertain. If they diverge wildly, you know that the weather is inherently unpredictable for the time horizon you are considering. This is the essence of modern weather forecasting. It is not about certainty, it is about probability. It is about understanding the limits of what we can know. Lorenz's discovery also had implications beyond meteorology. It revealed that chaos is not a failure of science. It is a fundamental property of the universe. Many systems are chaotic. The weather, the stock market, the flow of water, the orbits of planets. In all of these systems, tiny differences in initial conditions can lead to vastly different outcomes. This does not mean that these systems are random. They are governed by deterministic laws. But deterministic does not mean predictable. A system can be completely determined by its equations and still be impossible to forecast with precision. This was a profound shift in scientific thinking. For centuries, scientists had believed that the universe was like a giant clockwork mechanism. If you knew all the forces and all the positions, you could predict everything. The French mathematician Pierre-Simon Laplace had articulated this dream in the late 18th century. He imagined a demon who knew the exact state of every particle in the universe and could therefore calculate the past and the future with perfect accuracy. Lorenz showed that Laplace's demon was a fantasy. Even if the demon knew everything, it could not predict everything. Because the very act of knowing with infinite precision is impossible. Measurement always involves error, and in a chaotic system, error always grows. The butterfly effect became a cultural touchstone. It appeared in movies, in books, in popular conversation. It was a way of saying that small things matter, that our actions have consequences, that the world is more connected than we realize. But for meteorologists, the butterfly effect was something else. It was a constraint, a boundary, a reminder of humility. Before Lorenz, meteorologists dreamed of perfect prediction. After Lorenz, they understood that perfection was unattainable. But they also understood that they could do something useful. They could warn people about storms. They could help farmers plan their harvests. They could save lives. This is the paradox of weather prediction. We can never know the future with certainty, but we can know enough to change it. In the decades after Lorenz's discovery, meteorologists refined their models. They built supercomputers capable of running millions of calculations per second. They launched satellites that could see the entire planet at once. They deployed sensors across the oceans and the poles. They gathered more data than anyone had ever dreamed possible. And with all this data, with all this computing power, they did something remarkable. They extended the range of accurate weather prediction. In the 1980s, a 3-day forecast was considered reliable. Today, a 7-day forecast is often accurate, and even at 10 days, the models can sometimes identify broad patterns. But the limit remains. Beyond about 2 weeks, the butterfly effect takes over. The tiny errors that are unavoidable in any measurement grow until they dominate the forecast. The models diverge. The predictions become meaningless. This is not a failure. It is a feature. It is a property of the atmosphere. It is the way the universe works. And it is beautiful in its own way. It reminds us that the world is not a machine. It is alive, dynamic, endlessly creative. It is full of surprises. It is never predictable. Lorenz spent the rest of his career studying chaos. He identified patterns in chaos. He found that even in the midst of unpredictability, there is structure. He discovered what he called strange attractors, geometric shapes that describe the long-term behavior of chaotic systems. These shapes are infinitely complex. They are never exactly repeated, but they are recognizable. They are a kind of order within disorder. Lorenz died in 2008 at the age of 90. He never won a Nobel Prize. His work was not widely recognized outside of meteorology, but his ideas transformed our understanding of the world. Every time you check a weather forecast, you are seeing the butterfly effect in action. You are seeing the limits of prediction, and you are seeing the power of probability. The weather is chaotic. The future is uncertain. But we can still plan. We can still prepare. We can still hope. That is the message of Lorenz's work. That is the lesson of the butterfly. And that is where our story goes next. From the discovery of chaos to the construction of the modern forecasting machine. From the realization that prediction is impossible to the understanding that probability is enough. Because the weather does not care about our desire for certainty. It does what it does. It follows its laws. It creates its patterns. And we, with our computers and our satellites and our fragile understanding, try to keep up. We are not gods. We cannot see the future. But we can see enough to make a difference. And sometimes, that is enough. The discovery of chaos was a profound moment in the history of science. It revealed that the atmosphere, like so many natural systems, was fundamentally unpredictable in the long term. The butterfly effect was not a flaw in our models. It was a property of the universe itself. But there is a difference between knowing that perfect prediction is impossible and giving up on prediction entirely. Edward Lorenz had shown that we could never know the exact future. But he had not shown that we could know nothing about it. The future was uncertain, yes. But it was not random. There were patterns, there were probabilities, there were limits. And so the challenge shifted. The goal was no longer to predict the weather with certainty. The goal was to predict it with enough accuracy and enough lead time to save lives, protect property, and help people plan their days. The goal was to build the best possible forecast within the constraints that chaos imposed. To do that, we needed machines. Not machines that could do a few calculations quickly. We needed machines that could do billions of calculations, trillions of calculations every second. We needed supercomputers, and we needed data. Not just data from a few weather stations in populated areas. We needed data from everywhere, from the highest mountains and the deepest oceans, from the poles and the equator, from the surface of the Earth and from the stratosphere. We needed to see the whole planet at once. We needed satellites. This is the story of how we built the weather machine. The foundations had already been laid. Vilhelm Bjerknes had provided the theoretical framework in 1904. Lewis Fry Richardson had developed the practical methods in 1922, even though his calculations had failed. The equations were there. The method was there. All that was missing was the power to do the calculations quickly enough to be useful. Richardson had imagined a forecast factory, a vast hall filled with thousands of human computers, each calculating a small part of the globe, coordinated by a conductor in the center. It was a beautiful, mad vision, but it was also impossible. No human organization could coordinate 64,000 people fast enough to keep up with the weather. What Richardson needed was a machine. A machine that could do arithmetic faster than any human. A machine that could run for hours or days without getting tired. A machine that could store and retrieve millions of numbers instantly. The first such machine, the ENIAC, was built during World War II. It was enormous, filling a room 30 feet by 50 feet. It weighed 30 tons. It used 18,000 vacuum tubes. It consumed huge amounts of electricity. But it could do thousands of calculations per second, and that was enough. In 1948, a mathematician named John von Neumann, who had been involved in the ENIAC project, recognized that weather prediction was a natural problem for these new machines. He assembled a team at the Institute for Advanced Study in Princeton, New Jersey. The team was led by Jules Charny, a brilliant meteorologist who had done extensive work on simplifying the equations of the atmosphere. Charny's insight was crucial. The full equations of fluid dynamics were too complex for the computers of the late 1940s. But Charny realized that you could simplify them. You could filter out the small-scale features, the turbulence and the noise, and focus on the large-scale motions that drive the weather. The result was a simplified set of equations, known as the quasi-geostrophic equations, that were much easier to compute. In April 1950, Charny and his colleagues made the first successful numerical weather prediction. They used the ENIAC to calculate a one-day forecast. It took 24 hours to run. The computers were not yet fast enough to keep up with the weather, but the forecast was successful. It proved that numerical weather prediction was feasible. The dream of Bjerknes and Richardson had become a reality, but it was still a fragile reality. The early computers were slow, unreliable, and expensive. The models were crude, using coarse grids and simplified physics. The data was sparse, especially over the oceans and the poles. The forecasts were often wrong. Over the next decade, the technology improved. The computers got faster. The models got more sophisticated. The data network expanded. In 1954, the United States government created the Joint Numerical Weather Prediction Unit, bringing together the Weather Bureau, the Air Force, and the Navy to work on operational forecasting. By 1955, they were issuing numerical forecasts twice a day. These early forecasts were not always better than the human forecasters who had been doing the job for decades. The models were still too simple. The data was still too sparse. The computers were still too slow. But the trend was clear. The machines were getting better. And then came the satellites. On April 1, 1960, NASA launched a small, squat satellite named TIE-ROSE-1. It weighed 270 pounds. It carried 2 television cameras. It orbited the Earth at an altitude of 450 miles. It operated for only 78 days. But in those 78 days, it sent back 19,893 usable pictures of the Earth's cloud cover. TIE-ROSE-1 changed everything. For the first time, meteorologists could see the weather from above. They could watch entire storm systems forming and moving across the planet. They could track hurricanes from their birth to their landfall. They could observe patterns that were invisible from the ground. The satellite images were crude by modern standards. They were black and white. They were often fuzzy. But they were revolutionary. They revealed that the Earth's weather was not a collection of local phenomena. It was a single, interconnected global system. TIE-ROSE-1 was followed by a series of increasingly sophisticated satellites. Polar orbiting satellites circled the planet from pole to pole, providing global coverage. Geostationary satellites hovered over fixed positions, providing continuous views of specific regions. The satellites carried more instruments: infrared sensors for measuring temperature, microwave sensors for measuring moisture, radiometers for measuring radiation. The data from these satellites was fed into the numerical models. The models improved dramatically. The forecasters could now see the whole picture. They could predict the weather with increasing accuracy for increasing lead times. But the problem of chaos remained. The models were better, but they were still subject to the butterfly effect. Tiny errors in the data, no matter how small, would grow over time. The forecasts would eventually diverge from reality. The solution was elegant. Instead of running a single model once, you run it many times with slightly different starting conditions. You introduce small variations, consistent with the uncertainties in the measurements. You run the model 100 times, each time with different initial data. Then you look at the distribution of the results. This is ensemble forecasting. It was first proposed in the 1960s, but it took decades to become operational. The early computers were not fast enough to run multiple simulations. It was not until the 1990s that ensemble forecasting became a standard tool. Today, the major weather centers run ensemble forecasts every day. The European Centre for Medium-Range Weather Forecasts runs a 51-member ensemble. The National Centers for Environmental Prediction in the United States runs a 31-member ensemble. Each ensemble member is a slightly different version of the future. The spread of the ensemble tells you how confident you can be in the forecast. If all the members agree, the forecast is reliable. If they diverge, the forecast is uncertain. The ensemble forecast is not a single prediction. It is a probability distribution. It tells you the likelihood of different outcomes. That is why your phone app says 60% chance of rain. It is not indecision. It is honesty. It is a recognition that the future is uncertain and that we can only talk about probabilities. The development of ensemble forecasting was a major milestone. It transformed weather prediction from a deterministic art into a probabilistic science. It acknowledged the limits of predictability, but it also extended the range of useful forecasts. With ensembles, meteorologists could now provide reliable forecasts for 7 days, sometimes even 10 days. The weather machine was growing more powerful, but it was also becoming more fragile. The system depended on an enormous infrastructure: satellites, sensors, weather stations, supercomputers, communication networks. And it depended on international cooperation. The data from American satellites was used by European forecasters. The data from European satellites was used by American forecasters. The global forecast system was a shared resource. Andrew Blum, in his book The Weather Machine, describes this system as one of the most impressive achievements of human civilization. It is a triumph of science, technology, and global cooperation. But it is also fragile. The satellites can fail, the computers can crash, the cooperation can break down. Blum quotes a weather official who says, "We are in a golden age of meteorology. Our tools allow us to predict the weather more accurately than ever before, but we have not learned to trust them. And we cannot guarantee the fragile international alliances that make the system work." This is a paradox. The weather machine is more powerful than ever, but it is also more vulnerable. A single satellite failure can create gaps in the data. A single computer failure can delay a forecast. A single political dispute can cut off the flow of data between countries. The weather machine is a human creation. It is built by people. It is maintained by people. It depends on human cooperation, and human cooperation is not guaranteed. The next chapter of our story is about the people who keep the weather machine running. The scientists, the engineers, the forecasters, the diplomats. The people who build and maintain this invisible infrastructure. The people who make the forecast possible. Because behind every forecast, every app, every warning, there is a community of people working together. They are scattered across the globe. They speak different languages, they work for different organizations, but they share a common purpose. They want to understand the weather and help people prepare for it. This is the human dimension of weather prediction. And it is as remarkable as the technology. The weather machine is a miracle of modern science, but it is also a product of human imagination, human determination, and human cooperation. It is a testament to what we can achieve when we work together. And it is fragile. Imagine for a moment that you are holding your phone, checking the weather. The screen shows a simple icon, a sun, a cloud, a raindrop. It displays a temperature, maybe 72 degrees. It tells you the chance of rain, perhaps 20%. It is all very clean, very simple, very reassuring. But behind that simple icon lies a world of astonishing complexity. A vast, invisible infrastructure that spans the entire planet. A global network of sensors, satellites, supercomputers and human beings, all working together to produce that one small piece of information. This infrastructure is so vast and so intricate that it is almost impossible to comprehend. It is one of the greatest achievements of human civilization, and yet we take it for granted. We see the icon, not the infrastructure. We see the forecast, not the decades of science and the billions of dollars that made it possible. Let us start with the sensors. There are tens of thousands of weather stations on the surface of the Earth. They are scattered across every continent, on remote islands, in deserts, on mountaintops, in the middle of oceans. Some are operated by government agencies. Some are operated by airports. Some are operated by volunteers who simply enjoy observing the weather. Each station measures temperature, pressure, humidity, wind speed, and wind direction. Many also measure precipitation. They transmit this data to regional centers, which forward it to global centers. The data is collected, quality checked, and fed into the models. But surface stations are only part of the picture. To understand the weather, you need to know what is happening above the surface. You need to know the vertical structure of the atmosphere. That is where weather balloons come in. Twice a day, at hundreds of locations around the world, a balloon is launched. It is filled with helium or hydrogen, and it carries a small instrument package called a radiosonde. As the balloon rises, the radiosonde measures temperature, pressure, humidity, and wind. It transmits the data back to the ground via radio. The balloon ascends at a rate of about 1,000 feet per minute. It reaches an altitude of about 100,000 feet before it bursts. By that time, it has traveled tens of miles downwind. It has sampled the atmosphere from the surface to the stratosphere. Weather balloons have been used for over a century. They are one of the oldest and most reliable tools in meteorology. But they have limitations. They are expensive. They are labor-intensive. They provide data only at a few points, at a few times each day. To fill the gaps, we need something more. We need satellites. The modern weather satellite is a marvel of engineering. It orbits the Earth at an altitude of 22,000 miles. It is constantly monitoring the planet, collecting data on temperature, humidity, cloud cover, wind speed, and much more. It can see the entire hemisphere at once. It can track storms as they form and move. It can detect changes in the ocean surface temperature that influence the development of hurricanes. There are two main types of weather satellites. Geostationary satellites orbit above the equator at a speed that matches the Earth's rotation. They appear to hang motionless in the sky. They provide continuous coverage of a fixed region. The United States has two geostationary satellites, GOES-16 and GOES-17, which cover the Americas and the Atlantic. Europe has a similar system called Meteosat. Japan has Himawari. Polar orbiting satellites follow a different path. They orbit from pole to pole, passing over different parts of the Earth at different times of day. They provide global coverage, but only at a specific time for each location. The United States has the Joint Polar Satellite System. Europe has the METOP system. Between them, these satellites provide a complete, continuous picture of the Earth's atmosphere. They are the eyes of the weather machine. But satellites and surface stations are not enough. The oceans cover 70% of the planet. They are vast, remote, and poorly observed. To understand the weather, you need to know what is happening over the oceans. That is where buoys come in. There are thousands of buoys floating in the world's oceans. Some are moored to the seafloor. Some drift freely. They measure temperature, pressure, wind, and waves. They transmit their data via satellite. They are the ears of the weather machine. And then there are the aircraft. Commercial aircraft carry sensors that measure temperature, wind, and turbulence. They transmit this data in real time. There are thousands of flights every day. Each one provides a vertical profile of the atmosphere. The data is fed into the models. The data network is vast and growing. Every day, the global weather system ingests over 100 million observations. It processes them in real time. It uses them to initialize the models. But data is useless without computers. And the computers that run the weather models are among the most powerful machines ever built. The European Centre for Medium-Range Weather Forecasts, known as ECMWF, operates one of the most powerful supercomputers in the world. It is located in Reading, England. It consists of thousands of processors working together in parallel. It can perform trillions of calculations per second. The models run on these supercomputers are not simple approximations. They are comprehensive simulations of the entire Earth's atmosphere. They divide the globe into a three-dimensional grid. At each grid point, they compute the temperature, pressure, humidity, and wind speed. They then advance the equations forward in time, step by step. The grid is getting finer every year. In the 1970s, the typical grid spacing was several hundred miles. Today, it is around 10 miles. In some models, it is even finer. The increased resolution allows the models to capture smaller-scale features like thunderstorms and frontal boundaries. But higher resolution comes at a cost. It requires more computing power. It requires more data. It requires more energy. The supercomputers consume enormous amounts of electricity. They generate enormous amounts of heat. They need dedicated cooling systems. The cost of running a major weather center is staggering. The United States spends over $1 billion per year on weather prediction. Europe spends a similar amount. It is a massive investment, but the benefits are even larger. Accurate weather forecasts save lives, protect property, and drive economic growth. So the system is vast, it is expensive, it is technically complex, and it is fragile. It depends on a delicate balance of factors. The satellites must stay in orbit, the sensors must keep working, the computers must keep running, the data must keep flowing. A single point of failure can disrupt the entire system. In 2003, a computer at the European Centre failed. It was a hardware failure. It took several days to restore the system. During that time, the European forecasts were degraded. The impact was felt across the continent. In 2012, a solar storm disrupted satellite communications. The data flow was interrupted. Forecasters had to rely on older data. The forecasts were less accurate. These incidents highlight a fundamental truth. The weather machine is a human creation. It is subject to human error, to equipment failure, to natural disasters. It is not invulnerable. It cannot be. And then there is the question of cooperation. The weather machine depends on data sharing. No single country has enough sensors, enough satellites, enough computing power to do it alone. The system is global. It requires global cooperation. In the 1960s, during the height of the Cold War, the United States and the Soviet Union agreed to share weather data. It was a small act of cooperation, but it had enormous consequences. It created the framework for the global weather system we have today. That framework is still in place. The World Meteorological Organization coordinates the sharing of data between countries. It has over 190 members. They are committed to open data sharing. They recognize that weather does not respect borders. But the commitment is voluntary. It could be broken. A country could decide to withhold its data. A political dispute could disrupt the flow of information. The system could collapse. Andrew Bloom, in his book The Weather Machine, describes this fragility. He points out that the global weather system is based on trust. It assumes that other countries will share their data. If that trust were broken, the system would fail. The weather machine is a miracle of modern science, but it is also a miracle of human cooperation. It is a testament to what we can achieve when we work together, and it is a reminder of how dependent we are on each other. Every time you check the weather on your phone, you are benefiting from the work of thousands of people, from hundreds of organizations, from dozens of countries. You are benefiting from decades of scientific research and billions of dollars of investment, and you are trusting that the system will keep working. That trust is not misplaced. The system is robust. It has been built with redundancy and resilience. It has survived solar storms, equipment failures, and political tensions. It is not perfect, but it is remarkably reliable. But it could be better. It could be more accurate. It could provide longer lead times. And to achieve that, we need to keep investing. We need to keep improving the models. We need to keep launching new satellites. We need to keep building faster computers. We also need to keep cooperating. We need to maintain the global data sharing. We need to protect the system from political interference. We need to ensure that the weather machine remains a global public good. The weather machine is one of the greatest achievements of human civilization. It is a triumph of science, technology, and international cooperation. It is also a reminder of our interdependence. We are all part of the same atmosphere. We all share the same planet, and the weather machine helps us understand it. There is a quiet revolution happening in the way we think about the future. For most of human history, the future was seen as something fixed, something written in the stars or determined by the gods. You could not change it. You could only accept it. Then science came along and offered a different vision. The future, science said, is not fixed. It is not written. It is the result of physical processes unfolding according to laws. If you know the laws, and you know the initial conditions, you can calculate the future. This was the vision of Laplace. This was the dream of Bjerknes and Richardson. But Lorenz showed that this dream was impossible. The future is not calculable with certainty. It is not determined. It is not fixed. It is probabilistic. This is a difficult idea to accept. We want certainty. We want to know what will happen. We want to plan our lives, make decisions, invest our money, raise our children. We want to believe that the future is knowable. But the weather tells us otherwise. The weather is the most familiar example of a probabilistic system. It is governed by deterministic laws. It follows equations. But it cannot be predicted with certainty. There is always a chance of rain, even when the forecast says sunny. There is always a chance of sunshine, even when the forecast says rain. This is not a failure of forecasting. It is a property of the atmosphere. The weather is inherently probabilistic, and we have learned to live with that. We carry umbrellas on sunny days. We plan outdoor events with backup options. We accept that the forecast is a probability, not a certainty. But this acceptance has taken time. It has required a fundamental shift in how we think about prediction. It has required us to abandon the dream of certainty and embrace the reality of uncertainty. The shift began with Lorenz, but it was carried forward by others. In the 1960s and 70s, meteorologists began to develop the tools of probabilistic forecasting. They realized that the best forecast was not a single number, but a range of possible outcomes. The forecast should tell you not just what is most likely to happen, but how likely each outcome is. This approach is called ensemble forecasting. It is the foundation of modern weather prediction. The idea is simple. You run your model many times, each time with slightly different starting conditions. You introduce small variations, consistent with the uncertainties in the measurements. You run the model 100 times, each time with different initial data. Then you look at the distribution of the results. If most of the runs predict rain, you can say with confidence that rain is likely. If the runs are split, you know that the forecast is uncertain. If they diverge wildly, you know that the weather is inherently unpredictable for the time horizon you are considering. This is the essence of ensemble forecasting. It is not about a single prediction. It is about a distribution of probabilities. It is about telling people not just what will happen, but how confident you are that it will happen. The ensemble forecast is a sophisticated tool. It requires immense computing power. It requires careful handling of the data. It requires a deep understanding of the physics. But it is also a powerful tool. It provides more information than a single deterministic forecast. It allows people to make better decisions. Consider a farmer planning to harvest a crop. If the forecast says there is a 60% chance of rain tomorrow, the farmer can decide whether to harvest today or wait. The decision is not based on a single prediction. It is based on a probability. The farmer can weigh the risks and make a judgment. Consider an airline planning a flight. If the forecast says there is a high probability of thunderstorms along the route, the airline can reroute the flight or delay it. The decision is based on probabilities. It is not a guess. It is a calculation. Consider a city preparing for a hurricane. If the forecast says there is a 70% chance of landfall within 100 miles, the city can order evacuations. The decision is based on probabilities. It is not a panic, it is a measured response. Probabilistic forecasting is not a retreat from science, it is a refinement of science. It is a recognition that the world is complex, that our knowledge is incomplete, and that we must make decisions in the face of uncertainty. But probabilistic forecasting is also a challenge. It requires people to understand probabilities. It requires them to think in terms of likelihoods, not certainties. It requires them to accept uncertainty. This is not easy. People want certainty. They want simple answers. They want to know whether it will rain or not. They do not want a percentage. But percentages are honest. They reflect the reality of the atmosphere. They acknowledge that we cannot predict the future with certainty. They provide the best possible information. This is the philosophy of modern meteorology. It is a philosophy of humility. It accepts the limits of prediction. It acknowledges the chaos of the atmosphere. It respects the complexity of the system. But it is also a philosophy of power. It recognizes that even with the limits we can do a lot. We can provide reliable forecasts for a week. We can warn people about storms. We can save lives. The paradox of modern weather prediction is that we know more than ever, but we are also more aware of our ignorance. We have better models, more data, faster computers. But we also understand that the atmosphere is fundamentally unpredictable in the long term. We can see further, but we also see the limits more clearly. This is the reality of living in a chaotic universe. We are not gods. We cannot see the future, but we can see enough to make a difference, and that is a remarkable achievement. It is a testament to human ingenuity, human determination, and human cooperation. It is a triumph of science, but it is also a reminder of our limits. We cannot control the weather. We cannot predict it with certainty. We can only prepare for it. The future is not written. It is not fixed. It is a range of possibilities, and our job is to navigate those possibilities, to make the best decisions we can with the best information we have. This is the lesson of probabilistic forecasting. It is a lesson in humility. It is a lesson in wisdom. It is a lesson in courage. Because making decisions in the face of uncertainty takes courage. It takes courage to act on a probability. It takes courage to trust a forecast. It takes courage to accept that you cannot know everything. But that is the human condition. We live in a world of uncertainty. We make decisions every day without knowing the outcome. We take risks. We hope for the best. We prepare for the worst. And the weather is no exception. It is part of the fabric of our lives. It shapes our plans, our moods, our memories. It is a constant companion, always present, always changing, and we have learned to understand it, not perfectly, but enough. Enough to live with it, enough to prepare for it, enough to respect its power and its beauty. This is the story of weather prediction. It is a story of human ambition and human limitation. It is a story of science and of art. It is a story of probabilities and possibilities. It is a story of how we learn to live with uncertainty, and that is a story worth telling. There is something deeply human about weather. It is not just a physical phenomenon. It is a presence in our lives, a character in our stories, a companion on our journey. We talk about it constantly. We complain about it. We celebrate it. We remember it. Think about the conversations you have had today. How many of them mentioned the weather? The friend who asked if you brought an umbrella. The colleague who said, "Can you believe this heat?" The family member who mentioned the storm that is coming tonight. Weather is the universal small talk. It is the thing we all share, the common ground between strangers. It connects us to each other and to the world around us. But weather is more than small talk. It is also memory. The day you got married, was it sunny or rainy? The day your child was born, was it warm or cold? The day you moved to a new city, was there a storm on the horizon? Weather marks the moments of our lives. It is the backdrop to our stories. It shapes our memories in ways we do not always recognize. And weather is also emotion. A grey, rainy day can make us feel melancholy. A bright, sunny morning can lift our spirits. A sudden thunderstorm can make us feel exhilarated or anxious. The weather affects our mood, our energy, our sense of well-being. This is not just a psychological effect. It is physiological. The weather changes the way our bodies function. High pressure can make us feel alert. Low pressure can make us feel drowsy. Humidity can make us feel sluggish. Cold can make us feel tense. We are part of the weather. We are not separate from it. We are embedded in it. We breathe the same air that moves across the planet. We feel the same wind that shapes the clouds. We are part of the same system. This is the deeper truth that the physics of weather reveals. We are not observers of the weather. We are participants in it. We are part of the atmosphere, not apart from it. And this recognition changes everything. It changes how we think about weather. It changes how we think about ourselves. It changes how we think about our place in the world. Consider the ancient Greeks. They did not see weather as a physical system. They saw it as the will of the gods. Zeus controlled the thunder. Poseidon controlled the sea. Aeolus controlled the wind. Weather was a manifestation of the divine. This was not ignorance. It was a different way of understanding the world. It was a way of making meaning out of the chaos. It was a way of connecting the physical to the spiritual. We have moved beyond that. We understand weather as physics, but we have not lost the sense of wonder. We still look up at the clouds and feel something. We still watch a sunset and feel awe. We still feel the wind on our skin and feel alive. The physics of weather does not diminish this wonder. It deepens it. When you understand how a cloud forms, you see it differently. You see the invisible processes behind the visible shape. You see the thermodynamics, the condensation, the latent heat. You see the beauty of the physics. This is the gift of science. It does not take away the poetry. It adds to it. It reveals a deeper order, a hidden structure. It shows us that the world is more beautiful than we ever imagined. And it gives us a new way of telling stories. The old stories were about gods and heroes. The new stories are about atoms and equations. But they are still stories. They are still about the human search for meaning. Andrew Blum, in his book The Weather Machine, writes about the people who built the modern forecasting system. He calls them the priests of the atmosphere. They are the ones who interpret the invisible signs. They are the ones who read the runes of the data. They are the ones who tell us what the weather will do. This is not a mystical calling. It is a scientific one, but it has a mystical quality. The forecasters are intermediaries between the chaotic atmosphere and the human world. They translate the language of physics into the language of everyday life. The forecast is a story. It is a narrative about the future. It has a beginning, a middle, and an end. It has characters, the high-pressure system, the cold front, the storm. It has plot twists, the sudden change in wind direction, the unexpected drop in temperature. It has a moral. Be prepared. This is why we listen to the forecast, not just because we want to know whether to bring an umbrella, but because we want to know what is coming. We want to understand our place in the story. We want to be part of the narrative. The weather forecast is one of the few remaining shared narratives in our fragmented world. It is something that millions of people experience at the same time. It is a common reference point. It is a reminder that we are all subject to the same forces, the same winds, the same rains. And this is a powerful thing. In a world that is often divided, the weather connects us. It reminds us that we are not separate. We are part of the same system. We breathe the same air. We feel the same sun. We are all in this together. This is the deeper meaning of the weather. It is not just about physics. It is about connection. It is about the shared experience of being alive on this planet, under this sky. And that is something worth celebrating. The next time you feel the wind on your skin, take a moment. Feel the air moving. Feel the energy. Remember that this wind has traveled across oceans and continents. It has been part of storms and calms. It has touched other people, other places, other lives. And now it is touching you. You are part of the story. There is a question that follows every conversation about weather. It is the question that comes after the forecast, after the small talk, after the report of a storm or a heat wave. It is the question that scientists have been asking for decades, and it is the question that has become more urgent with each passing year. That question is this: is this normal? Is this heat wave normal? Is this storm normal? Is this drought normal? Is this the weather we have always had, or is something changing? To answer this question, you have to understand a distinction that is both simple and profound. The the distinction between weather and climate. The weather is what happens today. It is the temperature outside your window, the wind in your face, the rain on your roof. It is immediate, local, and always changing. It is the mood of the atmosphere, not its personality. Climate is something different. Climate is the long-term average of weather. It is what you expect, not what you get. It is the personality of the atmosphere, the pattern that emerges over decades and centuries. It is the sum of all the weather that has come before. The classic way to think about this distinction is this. Climate is what you expect. Weather is what you get. You expect July to be hot. You expect January to be cold. You expect the monsoon to come in June and the snow to fall in December. That is climate. But if July is hotter than usual, if the monsoon comes late, if the snow falls in April, that is weather. The distinction is not just semantic, it is essential. Because a single hot day does not mean the climate is changing, a single cold snap does not mean it is not. Climate is the signal, weather is the noise, and to understand the signal you have to look past the noise. This is why scientists define climate as the average weather over a period of 30 years. 30 years is long enough to smooth out the year-to-year variations. It is long enough to see the underlying trend. It is long enough to distinguish between a run of bad luck and a fundamental shift in the system. But 30 years is not forever. Climate changes. It has always changed. The Earth has gone through ice ages and warm periods, long cycles of heating and cooling that have shaped the planet and the life on it. These changes were driven by natural forces, variations in the Earth's orbit, changes in solar output, volcanic eruptions. They were slow, unfolding over thousands or millions of years. What is happening today is different. The changes we are seeing are fast. They are happening in decades, not millennia, and they are being driven by something new, human activity. This is the reality of climate change. It is not a distant threat. It is not a hypothetical. It is happening now, and it is being felt in every corner of the planet. And it raises a profound question. How do we know? How do we know that a particular heat wave or storm or drought is caused by climate change? How do we separate the signal from the noise? This question is the subject of a field of science called extreme event attribution. It is a relatively new field, and it is one of the most active areas of climate research. Its goal is to determine whether, and to what extent, human-induced climate change has influenced a specific extreme weather event. There are two main approaches to this question. The first is the probabilistic approach. In this approach, scientists run climate models many times under two different scenarios: the world as it is, with human influence, and the world as it would have been without human influence. They compare the probabilities of the event under both scenarios. If the event is significantly more likely under the human-influenced scenario, they can say that climate change played a role. This is a powerful method, but it has limitations. It is good at answering questions about the likelihood of an event, but it is less good at answering questions about the severity of the event. It tells you how much more likely the event was. It does not tell you how much more intense it was. The second approach is the storyline approach. This is a newer method, and it has gained prominence in recent years. Instead of focusing on probabilities, the storyline approach focuses on the event itself. It takes the specific, historic extreme event and asks, what would this event have looked like if climate change had not happened? This is a different kind of question. It is not about probability, it is about physics. It is about taking the actual weather pattern that produced the event and re-simulating it under different climate conditions. It is about asking, given this same circulation pattern, how much worse was the event because of climate change? This approach is called spectrally nudged storylines. It works by constraining the large-scale atmospheric circulation in a climate model to follow the actual circulation that occurred during the event. This ensures that the model reproduces the specific sequence of weather that produced the event. Then, the model is run again with different background climate conditions, one with the actual level of greenhouse gases and one with a counterfactual level representing a world without human influence. The difference between these two simulations reveals the contribution of climate change to the event's intensity. It tells you how much hotter the heat wave was, how much more rain the storm dumped, how much drier the drought became. This method has been used to analyze several recent extreme events. In one study, researchers used spectrally nudged storylines to analyze the European heatwave of 2022. They found that anthropogenic climate change had increased the intensity of the heatwave by an average of 1.25 degrees Celsius and locally by as much as 5.7 degrees Celsius. That is a tangible number. It is not a probability. It is a quantification. It tells you that the heat wave was not just more likely because of climate change. It was worse. It was hotter. It was more dangerous. This is the power of the storyline approach. It makes climate change concrete. It takes it out of the realm of statistics and puts it into the realm of experience. It says, this event, which you lived through, which you remember, was made worse by human activity. This is not an abstraction, this is real. And this matters. It matters because people do not experience probabilities, they experience events. They remember the heat that broke records. They remember the flood that washed away their homes. They remember the storm that changed their lives. And when you can tell them that these events were made worse by climate change, you are telling them a story that is grounded in their own experience. This is the shift that the storyline approach represents. It is a philosophical shift in climate science. It is a move from asking, how much more likely, to asking, how much worse? It is a move from abstraction to concreteness. It is a move from statistics to story. And it is a powerful tool for communication. As one researcher put it, spectrally nudged storylines represent a philosophical shift in climate science. They embrace the fact that people don't experience probabilities, they experience events. And when those events devastate lives, what matters is not an abstract change in likelihood, but the tangible role of human-driven warming in making them worse. This is not to say that probabilities are not important. They are. They are essential for understanding the overall risk. But they are not the whole story. They do not capture the lived experience of a disaster. They do not answer the question that people ask when they emerge from their homes after a storm. Was this caused by climate change? The storyline approach provides a different kind of answer. It says, yes, this event was influenced by climate change, and here is how much, and here is why. This is a powerful way to communicate the reality of climate change. It anchors the science in the memory of events. It makes the abstract concrete. It makes the distant immediate. It makes the invisible visible. And it matters now more than ever. Because the weather is changing, the climate is changing, and the events that we once thought of as rare are becoming more common. The heat waves are getting hotter, the storms are getting stronger, the floods are getting deeper. We need to understand why, and we need to tell that story. We have traveled a long way together, from the ancient lore of farmers and sailors to the elegant equations of Bjerknes, from the heroic failure of Richardson to the humble wisdom of Lorenz, from the vast infrastructure of the weather machine to the honest uncertainty of probabilistic forecasting. We have seen how human beings have learned to understand the sky. But now it is time to return to where we began, to the sky above us, to the air we breathe, to the wind on our skin. Because the weather is not just a problem to be solved, it is not just a system to be modeled. It is not just a set of equations to be computed. It is the very medium of our existence. It is the atmosphere that sustains us, the air that fills our lungs, the wind that carries the seeds of life across the planet. And there is beauty in it. There is wonder. There is mystery. Think about the air around you right now. You cannot see it, you cannot hold it, but it is there. It is pressing against your skin, it is flowing into your lungs. It is carrying the sound of my voice to your ears. It is the invisible medium of your life. This air is not empty. It is full of molecules, trillions upon trillions of them, all moving at incredible speeds, colliding with each other, bouncing off your skin, carrying energy from one place to another. It is a seething, roiling, restless ocean of atoms, and it is utterly invisible. This is the paradox of weather. It is the most visible and the most invisible thing in our lives. We see the clouds, we feel the wind, we taste the rain. But the system that produces these things, the physics that drives them, is hidden from us. It is a vast, invisible machinery working silently above our heads. And yet, we have learned to see it. We have built instruments that detect what our senses cannot, barometers that measure the weight of the air, thermometers that measure the heat of the molecules, satellites that capture the dance of the clouds, computers that model the flow of the atmosphere. We have made the invisible visible. We have turned the mystery into knowledge. We have turned the law into laws. But we have not lost the wonder. If anything, we have gained it. Because when you understand the physics, you see the beauty more clearly. When you know how a cloud forms, you see it differently. You see the invisible processes behind the visible shape. You see the thermodynamics, the condensation, the latent heat. You see the poetry of the physics. Consider a single raindrop. It is a tiny sphere of water, a fraction of an inch across. It seems simple, almost insignificant. But that raindrop has traveled a journey that spans the entire planet. It began as a molecule of water in the ocean, evaporating under the heat of the sun. It rose into the atmosphere, carried by a thermal. It cooled and condensed, joining billions of other molecules to form a cloud. It grew, through the process of coalescence, until it became heavy enough to fall. And then it fell, through thousands of feet of air, to land on your roof, your window, your face. That raindrop has been part of the ocean, the sky, the wind. It has traveled across continents and over mountains. It has been through the cycle of evaporation, condensation, and precipitation. It has been part of the great hydrological machine that powers the weather. And now it is here, on your roof. It is a tiny ambassador from the atmosphere, a messenger from the sky, and when you hear it fall, you are hearing the voice of the weather. This is the wonder of weather. It is not just a system, it is a journey, it is a story. It is a continuous, unfolding narrative of energy and matter, of heat and moisture, of wind and water. It is the story of the planet. And we are part of that story. We are not separate from it. We are embedded in it. We breathe the air that has traveled across oceans. We feel the wind that has shaped the mountains. We drink the water that has fallen from the clouds. We are part of the weather. This is the insight that the physics of weather reveals. It is not a cold, mechanical truth. It is a warm, living truth. It is a truth that connects us to the planet, to the sky, to the cosmos itself. When you stand outside and feel the wind on your skin, you are not standing apart from the world. You are standing in it. You are part of it. The wind is not something that happens to you. It is something that happens with you. You are part of the system. And this is a comforting thought. It means that we are not alone. It means that we are part of something vast and beautiful. It means that the weather is not an enemy to be conquered, but a companion to be understood. This is the gift of science. It does not take away the wonder, it adds to it. It reveals a deeper order, a hidden structure. It shows us that the world is more beautiful than we ever imagined. And it gives us a new way of living with the weather. Not as a threat, but as a presence. Not as a problem, but as a partner. So the next time you feel the wind on your skin, take a moment. Feel the air moving. Feel the energy. Remember that this wind has traveled across oceans and continents. It has been part of storms and calms. It has touched other people, other places, other lives. And now it is touching you. You are part of the story. There is a strange paradox at the heart of modern weather forecasting. We have never been better at predicting the weather. Our models are more accurate than ever. Our data is more comprehensive than ever. Our lead times are longer than ever. And yet, we have never been more skeptical of the forecast. Think about it. When you check the weather on your phone, do you really believe it? Do you trust that it will rain at 3 o'clock? Or do you check the sky yourself just in case? Do you carry an umbrella even when the forecast says sunny, just to be safe? This is the paradox. The better we get at prediction, the less we seem to trust it. The more we know, the more we doubt. The more certain the science, the more uncertain we feel. Why is this? Partly it is because of the nature of the forecast itself. The forecast is probabilistic. It says 60% chance of rain. It does not say it will rain. It leaves room for doubt. And doubt is uncomfortable. We want certainty. We want to know. We want a simple answer. Partly it is because we have been burned before. We have all had the experience of a forecast that turned out to be wrong. We planned a picnic, and it rained. We left our umbrella at home, and we got soaked. These experiences linger. They shape our expectations. They make us cynical. Partly it is because the weather is personal. It is not like a distant election or an economic report. It is immediate. It is on our skin. It is in our face. When the forecast is wrong, we feel it, and we remember. But there is something deeper at work. It is a crisis of trust. Not just trust in the forecast, but trust in the institutions that produce it. Trust in science. Trust in experts. Trust in the idea that we can understand the world and use that understanding to make our lives better. This crisis of trust is not unique to meteorology. It is a feature of our time. We are living in an age of skepticism, an age of doubt. We question everything. We believe nothing. We are suspicious of authority, wary of expertise, cynical about knowledge. And this is a problem, because the weather machine depends on trust. It depends on us believing the forecast. It depends on us acting on it. It depends on the fragile bond between the forecasters and the public. Andrew Bloom, in his book, The Weather Machine, writes about this crisis. He describes how forecasters struggle to communicate uncertainty. They know that the forecast is a probability. They know that it is not a certainty. But they also know that people want certainty. They want a simple, clear message. They do not want to hear about ensemble spreads and confidence intervals. So forecasters face a dilemma. They can be honest and say, there is a 60% chance of rain. But then people might not take the forecast seriously. They might not bring an umbrella. They might not change their plans. They might get wet and complain that the forecast was wrong. Or they can be decisive and say, it will rain. But then they are overstating their confidence. They are pretending to know something they do not know. And when the rain does not come, people will be angry. They will feel misled. They will trust the forecast even less. There is no easy answer to this dilemma. It is a deep challenge. It is a challenge of communication, of education, of culture. It is a challenge that requires us to rethink what we expect from a forecast. Perhaps we need to change our expectations. Perhaps we need to stop looking for certainty and start looking for information. Perhaps we need to understand that a forecast is not a promise, it is a tool. It is a way of making decisions in the face of uncertainty. This is not a retreat from science, it is a refinement of science. It is a recognition that the world is complex, that our knowledge is incomplete, and that we must make decisions in the face of uncertainty. It is a recognition that the best forecast is not the one that is always right. It is the one that helps us make better decisions. This is the philosophy of modern meteorology. It is a philosophy of honesty. It is a philosophy of humility. It is a philosophy of respect for the complexity of the system. But it is also a philosophy that requires trust. It requires us to trust that the forecasters are doing their best. It requires us to trust that the models are reliable. It requires us to trust that the data is accurate. And that trust is fragile. It can be broken. It can be eroded. It can be destroyed by a single high-profile failure, a single mistake, a single moment of overconfidence. This is why the weather machine is not just a technical achievement. It is a social achievement. It is a product of human cooperation and human trust. And it depends on maintaining that trust. The next time you check the weather, take a moment. Think about the people who made that forecast possible. The scientists who developed the models, the engineers who built the satellites, the technicians who launched the balloons, the diplomats who negotiated the data sharing, the forecasters who interpreted the results. They are all part of a vast, invisible community. They are all working together to give you a single piece of information, and they are all depending on your trust. So trust them. Not blindly, not uncritically, but trust them. Trust that they are doing their best. Trust that they are working with the best data, the best models, the best methods. Trust that they are trying to help you make better decisions. And when the forecast is wrong, do not give up. Do not lose faith. Remember that the weather is chaotic, that it is impossible to predict with certainty, that even the best forecast will sometimes be wrong. Remember that the forecast is not a promise, it is a probability, it is a guide. And remember that the forecasters are human too. They are doing the best they can with the tools they have. They are working in the service of something larger than themselves. They are trying to make the world a safer, better place. This is the bond of trust. It is the fragile bond that holds the weather machine together. It is the bond between science and society. It is the bond between the people who know and the people who need to know. And it is worth protecting. We have explored the paradox of prediction. We have seen how the weather machine works, how it depends on trust, how it is both powerful and fragile. And now we come to the final chapter of our journey. It is a chapter about hope. Hope that we can continue to improve our understanding. Hope that we can maintain the fragile bond of trust. Hope that we can live wisely with the weather and with each other. It is the conclusion of our story and the beginning of a new one. We have come a long way together, through the ancient law and the modern equations, through the heroic failures and the quiet triumphs, through the vast infrastructure and the fragile trust. We have seen how human beings have learned to understand the sky. And now we stand at a horizon. It is the horizon of what we know and what we do not know. It is the horizon of what we can do and what we cannot do. It is the horizon of hope. There is a word that has appeared in this story many times. It is a word that captures the spirit of this entire journey. The word is understanding. We have been trying to understand the weather. We have been trying to understand the physics, the chaos, the infrastructure, the probabilities, the trust. We have been trying to understand our place in the system. Understanding is a powerful word. It is not the same as knowledge. Knowledge is facts. Understanding is meaning. Knowledge is knowing that the air has weight. Understanding is feeling that weight on your skin. Knowledge is knowing that the butterfly effect makes prediction uncertain. Understanding is accepting that uncertainty with grace. This is what we have been building. Not just knowledge, but understanding. Not just data, but meaning. Not just a forecast, but a relationship with the weather. And this is the foundation of hope. Because understanding gives us the power to act. It gives us the power to prepare, to adapt, to respond. It gives us the power to make decisions that matter. Think about what we have learned. We have learned that the weather is a global system. It is not just local. It is not just regional. It is planetary. The air you breathe has traveled across oceans. The rain that falls on your roof has traveled across continents. The wind that rustles your leaves has traveled across hemispheres. We have learned that the weather is chaotic. It is sensitive to small changes. It is fundamentally unpredictable in the long term. And we have learned to live with that uncertainty. We have learned to think in probabilities. We have learned to make decisions in the face of the unknown. We have learned that the weather is connected to the climate. And we have learned that the climate is changing. It is changing because of human activity. It is changing in ways that are already affecting our lives. And it will continue to change, no matter what we do. But we have also learned that we can act. We can reduce our emissions. We can adapt our infrastructure. We can prepare our communities. We can build a better future. This is the horizon of hope. It is the possibility that we can shape our future, even in the face of uncertainty. It is the possibility that we can use our understanding to make a difference. It is the possibility that we can leave a better world for our children. This is not a naive hope. It is a realistic hope. It is grounded in science, in technology, in human ingenuity. It is grounded in the same spirit that drove Bjerknes and Richardson, Lorenz and Charney. It is grounded in the belief that we can understand the world and use that understanding to make it better. But it is also a hope that requires action. It is not enough to understand. We must act. We must reduce our emissions. We must invest in renewable energy. We must protect our forests and our oceans. We must build resilient communities. We must support the science that helps us understand the world. This is the challenge of our time. It is not just a scientific challenge. It is a human challenge. It is a challenge of will, of courage, of determination. It is a challenge that requires us to work together, across borders, across cultures, across generations. And it is a challenge that we can meet, because we have the tools, we have the knowledge, we have the understanding, we have the weather machine. But the weather machine is not just a machine, it is a symbol. It is a symbol of what we can achieve when we work together. It is a symbol of the power of science, the power of cooperation, the power of trust. And it is a symbol of hope. So let us hold on to that hope. Let us hold on to the belief that we can understand the world and make it better. Let us hold on to the belief that the future is not fixed, that we can shape it, that we can build a better world for our children. This is the message of the weather. It is not a message of despair. It is a message of hope. It is a message of possibility. It is a message that we can live with the weather and with each other in a way that honors the complexity and the beauty of the system. And that is a message worth carrying forward. We have reached the horizon of hope. We have seen what we can achieve. We have seen what we must do. And now we come to the final chapter of our journey. It is a chapter about returning to the ordinary, about the weather we experience every day, about the wind on our skin, the rain on our roof, the sun on our face. It is about finding wonder in the everyday and peace in the knowledge that we are part of something vast and beautiful. We have journeyed through the physics of weather. We have traced the arc from ancient lore to modern supercomputers. We have visited the laboratories of Torricelli and the battlefields where Richardson computed. We have stood on the mountain where the wind howls at 200 miles an hour and sat in the quiet office where Lorenz discovered the butterfly effect. We have seen the satellites spinning above us and the supercomputers humming below us. We have explored the infrastructure, the probabilities, the trust, and the hope. But now, we must return to where all journeys end, to the ordinary, to the everyday, to the sky above your window right now as you lie here in the quiet dark. Because this is where the physics of weather lives, not in the equations or the models or the satellites, but in the air you breathe, in the wind you feel, in the rain you hear, in the warmth of the sun on your skin. The ordinary sky is not ordinary at all. It is extraordinary. It is the stage on which the greatest drama of the planet unfolds. It is the medium of life itself. It is the atmosphere that sustains us, the air that fills our lungs, the wind that carries the seeds of the future. Think about the air in this room. It is not empty. It is full of molecules. Nitrogen, oxygen, argon, water vapor. They are all moving, all colliding, all carrying energy. They are all part of the same system that creates the clouds and the storms and the calms. That air has traveled. It has been over oceans and mountains. It has been part of hurricanes and gentle breezes. It has touched other people, other places, other lives. And now it is here, in this room, touching you. This is the wonder of the ordinary. It is not separate from the extraordinary. It is the extraordinary made familiar. It is the vastness of the atmosphere distilled into the air you breathe. It is the power of the wind distilled into the breeze that rustles your curtains. And this is the gift of understanding. When you understand the physics of weather, you see the ordinary differently. You see the hidden depth. You see the invisible structure. You see the beauty that was always there, but that you could not see before. Consider a cloud. Before you understood the physics, a cloud was just a cloud. It was a fluffy shape in the sky, something to look at and forget. But now you know. You know that a cloud is a vast collection of tiny water droplets, each one formed around a speck of dust or salt. You know that the cloud is the visible expression of an invisible process, the cooling of rising air, the condensation of water vapor, the release of latent heat. You know that the cloud is heavy, weighing as much as a jumbo jet, and you know that it is falling, slowly, steadily, back to the earth. Now when you look at a cloud, you see something different. You see the physics behind the poetry. You see the beauty of the process, not just the shape. This is the power of understanding. It does not take away the wonder, it adds to it. It reveals a deeper layer of beauty. It shows you that the ordinary sky is not ordinary at all. It is extraordinary. And this is true of all weather. The gentle rain that falls on your window is not just water. It is the culmination of a journey that began in the ocean, traveled through the atmosphere, and is now returning to the earth. The wind that rustles the leaves is not just moving air. It is the atmosphere trying to balance its temperature, to smooth out the differences between hot and cold. The warmth of the sun on your face is not just light. It is energy from a nuclear furnace 93 million miles away, traveling across the vacuum of space to touch your skin. This is the physics of weather. It is the story of energy and matter, of heat and moisture, of wind and water. It is the story of the planet, and it is the story of you, because you are part of it. You are not separate from the atmosphere. You are embedded in it. You breathe it. You feel it. You are it. This is the deepest lesson of our journey. We are not observers of the weather. We are participants in it. We are part of the same system that creates the clouds and the storms and the calms. We are part of the same flow of energy and matter that shapes the planet. And this is a comforting thought. It means that we are not alone. It means that we are connected to something vast and beautiful. It means that the weather is not an enemy to be conquered, but a companion to be understood. So, as you lie here, in the quiet dark, let the understanding settle. Let the physics become background. Let the equations fade. What remains is the ordinary sky, the sky above your window, the sky that has been there since you were born, and that will be there long after you are gone. It is the same sky that Torricelli measured, the same sky that Richardson computed, the same sky that Lorenz modeled. It is the sky that has inspired poets and farmers, scientists and sailors. It is the sky that holds the rain and the wind and the warmth. It is the sky that sustains you. And it is beautiful. Not because it is perfect, not because it is predictable, but because it is alive, because it is moving, because it is always changing, always becoming, always new. This is the weather. It is the breath of the planet. It is the pulse of the atmosphere. It is the voice of the sky. And now, as you drift towards sleep, let that voice be gentle. Let it be a lullaby. Let it carry you into the quiet dark, where the wind is soft, and the rain is a whisper, and the clouds are a blanket. You are part of the sky. You have always been part of it, and you always will be. So rest now. Rest in the knowledge that the atmosphere will keep moving, the wind will keep blowing, the rain will keep falling, and you will be part of it, as you have always been, as you will always be. Sleep well. The sky is watching over you. The end. Thank you for joining this journey through the physics of weather. If you enjoyed this slow, deep exploration, please consider liking the video and subscribing to the channel. It helps this quiet corner of science continue to grow. And remember, wherever you are, whatever the weather, you are part of something vast and beautiful. The sky is always with you. Good night.